Let's start with 3.05, which is components of functions. So this is just about identifying things as linear or quadratic and then finding some information about them. So what a linear function is it kind of says it in the name. And if we spell linear, well, our first four letters is line, which is a linear function. Is if it makes a line, it is a linear function. So it doesn't matter what your line looks like. It could be any shape it could go anywhere. It could look like this. It could look like this. We don't care, just as long as it's a straight line. And usually how we can tell that a function is linear is if we have something that looks like this, or equals y. So what we're looking at is our x. And our x, if it has something weird done to it, for example, 2x squared plus 3 equals y, then this is not going to be linear. But this is linear. If we have 2 square root of x plus 3 equals y, not linear, linear. So we're looking for x normally what you're used to seeing. If you see anything strange being done to x at any point, then it is a quadratic function. So this is useful because specific linear functions and quadratic functions have things in common with each other. So quadratic functions have things in common with other quadratic functions, and linear functions have things in common with other linear functions. So a quadratic function could look like anything, really, but probably what it's going to look like is something like this, just a bowl or an N or something like that. It's just going to be kind of circular on one side and it's going to open on the other side. And this is called a parabola. And some important things to know about this are things like this. This would be our minimum point.
Guess I won't go there.
Our minimum point right here is just the bottom of the parabola. So you think of it as if you come up from the bottom, are you going to hit the bottom of it or the top of it? And we're hitting the bottom part. So if it were facing the other way and we came up from the bottom, we would hit the top. So this is called a maximum. So you can also think of this as dropping something into a bowl. So if you dropped something into it, it would hit the bottom of the bowl. If you dropped something into it, it would hit the top of the bowl. The bowl's upside down. So this is more or less how you identify maximum or minimum. And usually with these, this is going to be your vertex too. So if we straighten this up and we make it how it should look, something like this, this is going to be our vertex and our minimum. And we can identify the point pretty easily. We can just count down how many ever. 1, 2, 3. And we can say, okay, this is 0 left and right, and then 3 down. So this is our vertex and our minimum. So an axis of symmetry. Symmetry is how things look on both sides. So if something is symmetric, it's going to look the same on both sides. So you can think of this as in you put a mirror down and it's kind of reflecting itself across through the mirror. So if we put a mirror, an imaginary mirror, right here, let me make this bigger. This is our mirror. And we're looking at this and we say, okay, well, this side is the same as this side for sure. They're reflecting across this mirror. we kind of have to use our intuition to think about where to put the mirror. So if we put the mirror right there, then we know that our axis of symmetry, which is the same way of saying where you put the mirror, is our x is our y-axis. I'm sorry. This is y, this is x. So we put the mirror down across a line, and then we just say, okay, that's our axis of symmetry. So if we had something that instead of like that looked like this, and we had our x-axis or our x-axis and our y-axis here, then our axis of symmetry is no longer our y-axis, it's now our x-axis. Same thing, because we just put the mirror down, we laid it down, and we look into it, and it looks the same on both sides. So these are things about quadratic functions that you're going to need to identify. The x or y intercepts are just places that it crosses each of these lines. It's the same as normal. So you look at where it crosses, a specific axis. So if it crosses the x-axis here, then it crosses it at 0. And if it doesn't cross the y-axis, so we say, okay, the x-intercept is 0, 0, and the y-intercept is nothing. So maybe we have another one that looks like this. Okay, we ask for x-intercepts and y-intercepts. So our y-intercept is going to be right here. So we're going to go down 1, 2, 3, 4.25-ish. I'm just trying to give you an idea of where it would be. This isn't an actual problem. And we did 0. So this is our y-intercept. And then our x-intercepts we have 2 of them, right here and right here. So we go up and we say -1, 2, 3. -3, 0. And +1, 2, 3. Again, 4.1 maybe. Again, I'm just kind of drawing this, and it's not, I know it doesn't work out exactly like it should, but this kind of gives you an idea of how to find each of these points. You just count over and you find where it crosses each axis. For linear functions, that's the same way for x and y intercepts, is we just look for a place where it crosses the y-axis. So we have our graph here, and our linear function goes like this. Then we're looking for this point and this point. So this is our y-intercept, and this is our x-intercept. So if we count down, we go 1, 2, 3, again, 3.25 maybe. And that's negative. So that will be our y-intercept, and then our x-intercept is up here. 1, 2, 3, 4, 5. So it is 5, 0. We just count over to that point, and we plot the point on the graph. So what it wants you to do in your assignment is it wants you to graph some of these, and you can graph them by hand, or you can use GeoGebra or whatever. And I encourage you to do it that way because it's going to be easier for you and it's going to take less time. So if we go through 1 or 2 of those, I'm going to go onto Symbolab and put in the graph, and then I will paste the graph in here and we'll find out the information we need to know about it. Okay, so let me get over to Symbolab real quick. Okay, it doesn't look like it's giving me a graph on Symbolab, so I am gonna go to GeoGebra. And I just type in the equation, which is x squared minus 2x okay. And now I am taking my screenshot and bringing it down here. Okay, so this is what it looks like when we graph it. You can do this by hand if you want. I think it's easier to just type it in the computer, but it is up to you. So now we're looking for some information. This is definitely a quadratic function because it's not a line. So okay, so for quadratic functions, identify the x and y intercepts, x and y intercepts, axis of symmetry, vertex as a maximum or minimum. Okay, so we need to answer all three of these questions. So we've already said is quadratic, so we're good to go on that part. So now we identify the x and the y intercepts. Well, if we look at it, we say, okay, well, it crosses the x-axis right here, and it crosses the y-axis right here. And then it crosses the x-axis again right there. So let's write those points out. So we say, okay, x intercepts are 0, 0, because that's where it's crossing this axis, and 2, 0. So our y-intercepts are where it crosses this axis. So we say, all right, well, it crosses right there again, so I'm just going to say 0, 0. So now we're looking for an axis of symmetry. And the axis of symmetry, where we lay the mirror down, is right here. Because on each side of this, it looks the exact same. So if we lay the mirror down right there, then we know that that is our axis of symmetry. Now we identify this point by going over 1 and saying, okay, well, x equals 1. So AOS, axis of symmetry, x equals 1. And now we need to identify maximum or minimum. And we can do that by imaginary dropping something into it. So if we drop something into this, it's going to hit the bottom of the bowl. So we know that this is a minimum. So we found out everything that we need to know about this specific graph. And we have answered number 1, part A, B, and C. And this looks like a lot, but it's all related. So it goes very quickly once you get in the hang of it and know what you're looking for. So I will work one more and then I'll leave the rest for you guys. So let's do number 4. So first off, let's try to identify it as quadratic or linear. So we have negative x squared plus 4x minus 3. So this is definitely quadratic because we have a regular x right there, and that would make me say, oh, it's linear, but we have this x squared right here. So we have something funny happening in an x somewhere. So that is what's going to make it quadratic. So if now that we've identified it as quadratic, we need to identify the same stuff. So I'm going to put the I'm going to put it in GeoGebra.
Excuse me, Mr. Albright.
Hello, Mari.
Hey, I'm gonna have to make this quick announcement, but it's gonna be funny to you, so it might chuckle you a little bit.
Okay.
The reason why I came in late, I was on the phone with Miss Ellis. Then I had to call the bus stop because my old bus driver had called the sheriff to my front yard because she thought there was something wrong because I was waving. So generally, I don't know what's going on, but it really scared me for a quick minute because they was all coming to my doorstep rushing and honking at the same time. So just to let you know, the reason why I'm here late because of that and because I was on the phone with Miss Ellis at the same time.
Well, I'm glad you're okay.
Okay, thank you.
Yeah, you're welcome. Okay, so we have our graph here. So let's worry about what we need to figure out. So we need x and y intercepts. We need maximum or minimum. And we need our axis of symmetry. Actually, this is not, wait. I'm sorry, it plugged in the wrong equation. So let me go back real quick and I will type it the right way. Okay, so let's ignore everything that I just did and think about this equation. Okay, so now we still need to find all of these things, and this one is quadratic. The other one was linear, but this is quadratic. So let's think about our x and our y intercepts. So we're crossing the x-axis here and here, and we're crossing the y-axis here. So I'm going to write those out. X-intercepts, this is x, this is y. So it crosses at 0, 1 and 0, 3. Our y-intercepts are I'm sorry, these the x-intercepts are backwards. They need to be this way. 1, 0 and 3, 0. Because we go left and right and then up and down. So our y-intercepts, on the other hand, are 0, -3. Because we don't move left and right and then we move down 3. So that's my bad. Now we think about the axis of symmetry. So if we put the mirror down right here, then that's going to work perfectly fine. And now once we've got the mirror down, we identify this point. So we say x equals 1, 2. We don't count that. So 1, 2. So we end up at x equals 2 for our axis of symmetry. And now we need to do maximum or minimum. So we drop something on top of it, and it is going to land on the very top. So we know that this is a maximum. And that is all the information we need to know about that one. So let's move on to the next lesson and see if we can get that one done. So 307 is about rate of change. And rate of change is like if you're going down the road and you're driving to Dothan and you are driving 60 miles an hour and you start speeding up and you go to 65 miles an hour. Your rate of change was 5 miles an hour. It wasn't 65, it was just how fast you changed. So we're talking about the quickness of the change, not necessarily how far you went. So if I'm walking and then I go to running really quick, my rate of change was very quick. But my rates are pretty steady. So if I'm going 60 miles an hour and then I'm going 65 miles an hour, those aren't changing, those aren't moving around very much. They're pretty steady right there. So rate of change is just talking about how quickly you are moving, I guess. It's not speed, it's the rate at which the speed changes. So for one of the first problems on your sheet, I'm trying to screenshot it and I will put it on the page. Okay. So let's just talk about this in normal people terms before we start talking about the math. So it says this is her trip to Washington, D.C., and this is how far she is from home, and this is the time. So she's moving, she's moving, she's moving, she's stopping, she's moving, she's moving, she's moving. So we say, okay, well, for which time period is the rate of change the greatest? Explain in complete sentences. So we're looking for how fast she was changing. And the rate of change this is not a rate of change from 9 to 11. That is steady. She's not changing her speed. She's driving a constant speed. There we go. Well, okay, so she's driving a constant speed from 9 to 11. But from 10 to 11, or from 10 to 12, she completely stops. So the rate of change goes up a lot because she goes from moving to not moving. And then she goes from not moving to moving again. So the rate of change goes up again. So the period for which the rate of change is the greatest will be this period here from it's at 12 right here. So from 11 to 1 or from 12 to 1 or however you want to say that. I don't know exactly what they're looking for here. But this is the highest rate of change because she is changing the quickest, not necessarily how fast she's moving. So we say, okay, for what time period is rate of change the least? Well, we have several times where it's the least. So it's not changing from here to here. It's not changing from here to here. It does change here, but then it doesn't change from here to here. It doesn't change from here to here. It changes here again, and it doesn't change from here to here. So the rate of change, for which period the rate of change is the least, I would probably say this because she's not moving at all, but she's also not changing. So maybe 11 to 12 or 9 to 11. The rate of change is steady. It stays the same. So what is the rate of change between 9 and 10 a.m.? Show your calculation. So let me look up what calculations exactly that they want on your lesson. And then maybe I will be able to walk through that. Give me 1 second, guys. Okay, guys. So what we need to do first is we need to write like a table of values, like we did in our lesson on Friday. And we already have all the information we need. We just need to write it. So if we go and we say X and Y, and we say this is 9 a.m., this is 10 a.m., this is 11, 12, 1, 2. And then on the right side, we just write the distances. So we just write where it is on the y-axis. So 9 is about 50. 10 is about 100. And I'm not being exact here on purpose. It's kind of close. So maybe 12 is, wait, I'm sorry. This is supposed to move down. And then, so 1 is maybe about, maybe 175. And then this is about 225. So if we work this, or I'm sorry, this goes with 50. So what we're looking for here is these, they all change by 1. So our rate of change on hours is 1. It's changing 1 hour every time. It's steady. But over here, we have 1, we have 50, 0. I'm sorry, this is not 1, this is 0. Here to here is 75. Here to here is 50, it looks like. Yeah. So now that we have that, we know a little bit more about how far she was going, and we can do better than this. We know that this is where she changed the greatest, because this number is the biggest. So if we say 75 for number 3, then that is going to be correct. So she changed the most between 12 and 1. Okay, so looking at another example. Okay, so we have this guy. So we have the daily high temperature in Placerville, California. from April 1st to April 7th. So now we're looking for which time period is the rate of change the greatest. So we're looking again for where it changes the most. So if we look here to here, it doesn't change very much. Here to here, it doesn't really change very much. Well, here to here actually does change a good bit. Here to here doesn't change very much. Here to here, again, that changes a good bit. And then here to here doesn't really change a lot. So it's pretty much between this and this. So to me, the one on the right looks a little longer, this one. So I'm going to say that that is where our rate of change is the largest. So which time period the rate of change is the greatest? I'm going to say from April 5th to April 6th. So if we look for the least rate of change, I'm thinking maybe this one or this one. Again, it looks like this one to me. So I would say that the least rate of change would be from here to here. So that kind of gives you an idea of what you're looking for here. Is you're looking for how far apart each day is, how much it changed each day. And where it changed a lot, that is a high rate of change. Well, where it changed a little, that's a low rate of change. So that is more or less rate of change. It's just talking about the difference between the high rate of change and the low rate of change and things like that. And I encourage you to watch the lesson on this because I know I haven't done the greatest job at covering exactly what they want you to know. So go through and watch the lesson and see if you can get this one done. And we can talk about it again a little bit on Wednesday. But I mean, again, we're pretty far ahead, so I'm gonna let you guys go. And if y'all can try to get through the rate of change lesson by Wednesday, then we can go over sequences on Wednesday, and then move on from there. So you guys have a great day, and I will talk to you soon.